Physical Review B, Volume 30, Number 4, August 15th, 1984. Robert L. Forward. Hughes Research Laboratories, Malibu, California, 90,265 quarts, and Air Force Rocket Propulsion Laboratory, Edwards Air Force Base, California, 93,523, received November 23, 1983, revised manuscript, received April 16, 1984. Any pair of conducting plates at close distances, less than 1 micrometer, experience an attractive Casimir force that is due to the electromagnetic zero-point fluctuations of the vacuum. A vacuum fluctuation battery can be constructed by using the Casimir force to do work on a stack of charged conducting plates. By applying a charge of the same polarity to each conducting plate, a repulsive electrostatic force will be produced that opposes the Casimir force. If the applied electrostatic force is adjusted to be always slightly less than the Casimir force, the plates will move toward each other and the Casimir force will add energy to the electric field between the plates. The battery can be recharged by making the electrical forces slightly stronger than the Casimir force to re-expand the foliated conductor. Casimir force. In 1948, Casimir predicted that the electromagnetic zero-point energy fluctuations of the vacuum should have observable effects on macroscopic objects. Specifically, he predicted that there would be an attractive force between two conducting plates. 1.2, the Casimir interaction energy per unit, area U, between two conducting plates separated by a distance A, and the resulting force per unit area, or pressure P, R. Id UHC equal to a 1440-3. F Dewey per dA 480A, where H equal to 6.626 1034, J second C minus 3, ECAR 108 meters, SEC. This is a fundamental force that exists in the vacuum between any pair of conductors that may be interpreted as a zero-point pressure of electromagnetic waves. Casimir's results were later expanded by Lifshitz to include forces between dielectrics. The force per unit area between two dielectric plates with a dielectric constant E when separated by a distance A is 3. The E, 1, if E 480A, E plus 1, 2, where F, E, is a function that tends to 1 when E is very large and 0.35 when E less than 4. The Casimir and Lifshitz equations take into account the retardation effects in the electromagnetic field. The equations apply down to separation distances corresponding to 1 radian of the shortest wavelength radiation A that interacts significantly with a conductor or delect 3 to 5 trick. Min. 2. When the separation is less than min, then the equation for the pressure reverts to the non-retarded force previously calculated by van der Waals and London between. Atoms. For two plates, the pressure, due to the unretarded electromagnetic vacuum fluctuation force, is equal to a FC6 Ray 3, where C is an empirical constant that depends upon the material in the plates. Second experimental verification of the Casimir force. The experimental measurement of the Casimir force has been attempted a number of times with varying degrees of success. Usually the experiment is carried out between a curved dielectric lens and a flat dielectric plate, or two crossed dielectric cylinders. The closest separation distance at which force levels have been measured was 1.4 nanometers using two crossed cylinders of mica. The data show good agreement with the one, a Lifshitz law from 30 to 20 nanometers, with a break in slope at 15 nanometers changing to a 1, a 3 London van der Waals law from 10 down to 1.4 nanometers. At a separation distance of 1.4 nanometers, the measured force between the two mica cylinders was over 10 kilonewtons per square meter. Good experiments on conducting plates have proved to be extremely difficult. Some recent experiments used conducting surfaces made of flat silicon crystal plates and amorphous silicon deposited on a glass lens. The force showed a 1, a dependence down to 300 nanometers. The data then deviated strongly, probably indicating a lack of surface smoothness. Thus, although experiments on dielectric plates are in good agreement with theory down to very short spacing and quite high force levels, there are no good experiments on metal plates down to the spacings, 120 nanometers, that would show the predicted deviation from the 1A Retarded field law to the 1. A. Non-retarded field law. If new experiments could be carried out that demonstrate the existence of the very strong forces that theory predicts for conductors at separation distances of 20 nanometers and below, then these forces may be a new source of energy. 30. 1700. The American Physical Society. 30. Extracting electrical energy from the vacuum by 1701. With recent advances in microcircuit technology, including the development of molecular beam epitaxy atomic spray guns that can lay down monolayers of atoms, it should now be possible to prepare samples of metals that are sufficiently flat to carry out Casimir force experiments at separation distances of less than a nanometer. As far as is known, however, no such experiments are being planned. Third, extraction of energy from the vacuum fluctuation fields. The Casimir force has some of the properties of the gravity force. It is purely attractive, independent of the material in the plates, and varies as the inverse power of the separation distance, although the variation with separation distance goes as a higher power than the gravity force. There is no rigorous proof known that the vacuum fluctuation field is a conservative field, such as the gravity field. It is highly probable that it is conservative, however, otherwise it would be possible to design machines using the Casimir force that would allow an infinite amount of energy to be extracted from the vacuum. Even if the vacuum fluctuation field is a conservative field, that does not mean we cannot use it to obtain energy. The gravity field of the Earth is a conservative force field, and yet hydroelectric dams extract energy from the gravity field by using water coming from a region of high gravitational potential. In reality, of course, the energy extracted from a hydroelectric dam came originally from the sun, which evaporated the water from the oceans at a low gravitational potential and placed it in lakes at a high gravitational potential. The hydroelectric dam is then seen as a mechanism that uses the gravitational force of the Earth as a catalyst to convert the gravitational potential energy of the water into kinetic energy that can in turn be converted into electricity by the turbines. Hydroelectric dams are also used for energy storage. During times of low electrical demand, electricity can be used to pump water back up to a lake at high gravitational potential. In the same manner, we can prepare a conductor in a foliated state, which is in a high vacuum fluctuation potential energy state due to its large surface energy. We can then use the Casimir force as a means to convert the potential energy into kinetic energy, as the foliated conductors cohere into a solid block of conductor that is in a low vacuum fluctuation potential energy state. The part of the hydroelectric turbines can be played by any mechanism that can convert kinetic energy into electricity. For this paper, we will use the electrostatic repulsion force between two conducting plates with the same polarity of charge. Fourth, vacuum fluctuation battery. We now propose a general concept for the construction of an aluminum foil vacuum fluctuation battery. A large number of leaves of ultra-thin aluminum foil are arranged in a stack with the leaves separated by a few micrometers. Each leaf is connected electrically to an active, bidirectional power supply, and the shape and position of the leaf is monitored by sensors. The power supply gives each leaf a small amount of positive charge. The positive charge will create an electrostatic repulsion between the plates that will keep the plates separated despite the attempt of the Casimir force to pull them together. This electrostatic suspension system is unstable, of course, so that the position of each leaf will have to be electronically stabilized by feedback from the position sensors through the active power supply. Stability may also be enhanced by unique geometries, or by partial mechanical support of the leaves using frames of insulating material such as aluminum oxide. The voltages applied to the end leaf and the next to the end leaf are then adjusted so that the electrostatic repulsion between these two leaves is lowered until the electrostatic force is slightly less than the Casimir force at that distance. The Casimir force will draw the two leaves together, doing work against the repulsive electric field between the plates. By adjusting the electric field to always be slightly less than the Casimir force, the active bidirectional power supply can extract electrical energy out of the plates as they move from large separation distances, where the vacuum fluctuation potential energy is near zero, to the minimum separation distance, where the vacuum fluctuation potential energy is large and negative. The process is repeated by the next leaf until the foliated conductor is condensed into a solid block. Alternately, all the leaves could be brought together at the same time, like compressing an accordion. Fig. 1. Spiral design for a vacuum fluctuation battery. 1702, Robert L. Forward. 30. Thus, by cohering the multitude of aluminum leaves in a foliated conductor into a single block of aluminum under the careful control of an electronic servo system, it is possible to extract electrical energy from the vacuum. If the collapse process is halted before the aluminum films cohere, then the vacuum fluctuation battery can be recharged by making the applied electrostatic force slightly larger than the Casimir force. The leaves will be pushed apart at the cost of supplying energy from the bidirectional power supply. Another version of the vacuum fluctuation battery that might be easier to fabricate and have more stability would be a wide, flat spiral of foil, see Figure 1, built along the lines of a Slinky TM toy. In this structure, there is only one conductor to be contacted, since each turn of the spiral acts against the neighbouring turns. The spiral configuration allows a substantial compaction of the foil from large spacings to small spacings while maintaining uniform spacing. Acknowledgements. This research was supported by Air Force Rocket Propulsion Laboratory Contract F04600 and 1183 C013 and Hughes Aircraft Company. Permanent address: HBG Casimir, Proc. K. Ned, Akkad, Wet, Amsterdam 51, 793, 1948. This reference is hard to obtain. Casimir's result is re-derived in an easily readable form in Harris, Ref 2. E. G. Harris, A Pedestrian Approach to Quantum Field Theory, Wiley Interscience, New York, 1972, 3 E. M. Lifshitz, SOV. Phys. GT 2, 73, 1956. Gs. Ex per Phys. 29.94, 1955. Plus HBG Casimir and D. Polder, Nature 158, 787, 1946. HBG Casimir and D. Polder, Phys. Reverend 73360, 1948. 6 J. H. van der Waals, Ph.D. Thesis, University of Leiden, 1873. 7 degrees Fahrenheit, London, Z-Phys. 60,491, 1930. 8 H. Hammaker, Physica, Utrecht, 4 1058, 1937. F. Whitman, H. Splitgerber, and K. Ebert, Z-Phys. 245,354, 1971. 10 J. N. Israelakvili and D. Tabor, Prokhor Sok, London. A 331-9, 1972. 11 W. Arnold, S. Hunklinger, and K. Dransfeld, Phys. Reverend B. 19, 6049, 1979. 21 1713 E. 1980.